Okay, here's some examples on work and energy problems from section 6.1 or chapter 6 out of your textbook. Okay, so if you have any questions about like any formulas or anything like that, that'll be in your notes. Okay, I won't be going over that here. Here's just kind of examples on how to do some of these problems. So the first one, the student lifts a box with a weight of 100 newtons from the floor. So again, always write down, so the force equals 100 newtons. Okay? And that's Fg because it's weight. So write down what you're given. Okay? So from the floor, which is a distance of 0.8, so our height is 0.850 meters, and carries it horizontally a distance of 4.5 meters across the room. Again, for work, this number doesn't matter. Okay, that's horizontally. Okay, it's like where our force is vertical, our height is vertical. Those are all that matter. So where is the work done? Is it in lifting the box or carrying of the box? So the work is done in lifting the box because that's the direction the force is going. So remember, for work, it's always force times the direction it's moving. So in this case, how much work is being done? So again, work formula equals work equals force times change in distance. In this case, it's the height. So it'd be 100 newtons times 0.850 meters, and we get 85.0 joules. Okay, and so work is also, it's measured in joules. Okay, one thing to kind of note there. Okay, for this next question, describe a situation where a force acts on an object, but there is no work done. Okay, and in the second situation, an object undergoes displacement, but no work is done. So the first situation really is like you have force but no work. Okay, if you have force but no work, that means, like according to our formula, force times distance, one of these has to be zero. So in this case, if we have a force and no work is done, there's no displacement. So like you're pushing against a big boulder, but it's not moving. You haven't overcome that force of friction. Okay, you might be pushing it with a lot of force until it starts moving and actually changes its displacement. Okay, you can you can put all the force on it you want until it reaches that enough to overcome friction. There's really no work being done. Okay, another second situation, an object undergoes displacement but no work is done. So that's similar to like when you are carrying a box. Okay, there's no force like that you're overcoming, so like over that distance. So when you lift up the box, yes, you're overcoming that force over a distance. Okay, but now I'm walking with it. Okay, the force is perpendicular to the displacement, and like another way to kind of say it is, if it's perpendicular, then it'd be, according to our formula, like force times cos of our angle. Our angle would be 90 degrees due to the force. And if you type in your calculator, cos 90 is actually equal to 0. So that would be an example of that second situation. Okay, question 3, a sketch shows a wagon that is pulled across a horizontal driveway by a child. The child pulls the handle of the wagon with a force of 55 newtons. So again, force equals 55 newtons. Okay, to overcome the force of kinetic friction acting against the motion. Okay, so basically what that's telling us is like, this is our net force. We don't have to look up the force of friction or anything like that. Okay, if the wagon moves a distance of 15 meters, find the work done. So our displacement is 15.0 meters. Okay, our formula. Okay, on our formula sheet, work is equal to force times cos of our angle times our change in displacement. Yeah, I just put in a different order, but like if you look on your formula sheet here, okay, this is the formula we're using. Force or work equals force times distance times cos of the angle. Doesn't really matter which order you put it in because you're multiplying them together. So force is 55.0 newtons. Cos of our angle 67.5, and times the distance of 15.0 meters. So I guess we'll put times in there. And our answer we get is 316 joules once it's rounded. Oh, not a picture there, but 316 joules. This next question, so like when an object is lifted vertically against the force of gravity, work is done against gravity. If the object is released and allowed to fall, gravity does work on the object to increase its velocity. And its kinetic energy, or energy of motion, or it's converted to that. So clearly lifting an object against gravity stores energy in some form. So name this type of form. So this is potential energy. The formula is EP equals mgh. It's all on your formula sheet, okay, and I went over this in your other set of notes. Okay, now we'll kind of show you how to use that formula, okay, which hopefully we mostly get. Okay, so for this one, find the change in potential energy when a box with a mass of 25 kilograms, okay, is lifted from the ground to a height of 1.5 meters. So our formula, change in potential energy, is equal to mass times g times change in height. Okay, this is our mass, this is our delta H, and then we know G is equal to 9.81. So we just put our numbers in, so 25.0 kilograms. Always make sure you're in kilograms, not grams. 9.81 meters per second squared, and 1.50 meters. And we get our delta EP is equal to 368 joules once we've rounded to 3 sigdigs. Okay, and so in your notes we talked about like having a reference point. That's what this next question's kind of dealing with. I got these stairs here. Here's our ground level is 2. Then we can go up a stair and up to 3 or up to 4. So like considering the sketch to the right, when calculating potential energy, the box is shown lifted from the ground level 2. So from here to here. Okay, calculate the change in potential energy when it's lifted that far. Okay, and so it's just again, EP equals mgh. Okay, put your numbers in. So our mass of our box is 15.0 kilograms times 9.81 times our height is 5 meters. And so our EP from, we'll say from 2 to 3 is equal to 736 joules. Okay. Next, so like we got the first one calculated from 2 to 3. Now we want to calculate it when it's going from 3 to 4. So EP from 3 to 4 is going to be same mass, same 9.81, and then it's times 7 meters. So our EP from levels 3 to 4 equals, okay, we got 1.03 times 10 to the 3 joules. Okay, again, anytime you're like this, 10 to the 3 is equal to a kilo, so that's what like you see here, it's just changed to kilojoules. Okay, which is just something that's easier to do. Yeah. Either way, like if you put 1.03 times 10 to the 3 joules or 1.03 kilojoules, you get it right. Just be aware, like if you're doing a quiz or a test, like what they're asking for your final answer. Okay, and then finally calculate the change in energy when the box is lifted directly from the ground level to level 4. And then does the total change in the potential energy from the ground to level 4 change, or does the total change if you go from the ground to level 3 then to level 4? So basically it's saying like, so if we have our potential energy of our mass times 9.81 times our total, like from the ground here to the top, so that's 12.00 meters. So our potential energy, we got 1.77 kilojoules. if we add these two numbers together, we also get 1.77, so the total doesn't change. So we just, and that's what it's saying is like the difference from here to here, it doesn't matter if you stop here, the potential energy at the top, okay, is equal, like when reference to the ground, will be equal to this. Okay, for this next one, so we're still considering this sketch here. Yeah, I'm just going to move this up. Okay, so consider the sketch to the right. What potential energy does it have at level 4 when measured with respect to level 1? So level 1's down here. Okay, and again, whenever it says like measured with respect to, that's saying that's the reference point or starting point. Okay, and so we'll start there. Okay, I'm going to do this and then I'll show you the answer just to shorten up this video a bit. Okay, so we just have 15 times 9.81 times 15 meters. So our total change 2.21 kilojoules. Okay, and then the second part asks us what will the box have in level 3 measured with respect to level 1. So we're just looking, we have a difference of 8 meters with respect to the level 1. So we get 1.8. And then it says, does it matter what you use as a reference point when calculating the potential energy? It does matter. Sorry, we missed this part first. It says, how is the change in potential energy between levels 3 and 4 compared to the value found in the previous question? It's going to be the same change no matter which, like where you're referencing it to. Like, again, if this is referenced to the ground to here, they're going to be the same. This from here to here will be the same. And then the total would be there. Okay, and then, yeah, so the reference does matter because that's going to change like this number here, and then that. But then if you add them all together, you'll get the total. Okay, these next two questions have to do with Hooke's law, okay, which is talked about in your notes. Okay, so we have a spring that's 25 centimeters long. Okay, this number is actually not needed. Okay, and it's always kind of handy to write that down. Like that's just saying how long the string is. Okay. Sometimes it's helpful because they'll say like the spring starts at 25 centimeters and then it is stretched to 30 centimeters. So then you'd need the difference, like your difference in position would then be 5 centimeters. So just be careful. Like in this case, it's not needed. Okay, we have a force of 40 newtons, so that's equal to F. Okay, applied to it, it stretches by 20 centimeters. So this is our X value here. Okay, and we need to change that to meters because our final answer, like our value of K, is in Newton meters. Okay, and so for meters, we're going to divide that by 100, so we get 0.20. Actually, should have 200 meters. Okay, what is the elastic K or constant K for the spring? So the formula we're going to use is force equals K times X. Okay, we're going to rearrange that. We want to solve for K, so K is going to equal X over F. Put our numbers in. So X is 0.200 meter. Sorry, I have this upside down here. This should be F over K. Because, right, you're going to divide both sides by K. Or by X, sorry, not. So K is equal to F over K, or F over X, and that's how we get our Newton meters. So just a quick thing to always check. So we got 40 newtons over 0.200 meters, and we get 200 Newton meters is our answer for K. Okay, a spring-operated ping pong launcher requires a force of 24 newtons to fully compress the spring, which has an elastic constant of 36 Newton meters. How far does the spring compress, and how much elastic potential energy does this compressed spring have? Okay, so first, like this is our force. Okay, this is our K value. So we have F equals K times X. Now we're looking for X. We're going to divide both sides by K. So X is equal to our force, 24.0 newtons, divided by 36.0 newtons over meters. And so our X value We get in meters, so 0.667 meters. And just to kind of give us a nicer answer, put in centimeters, so 66.7 centimeters. Okay, which we got over here. Okay, and then how much elastic spring potential do we have? So now we're using the formula so EP equals 1/2 kx squared. Let's put our numbers in. 1/2 k is 36 newtons. X is, we want to use the one from meters, not squared, and our potential energy that we get is 8.00 joules. Okay, so just knowing, again, right off the bat, the thing you want to start, label what you have. You can label it nicely over here like we've done before, or just as simple as this, so I know that like this is K, this is F, or for this one, like I didn't need this. Okay, that's always helpful to know those numbers, and so you aren't trying to use them. Okay, these last couple of questions are just to do with kinetic energy. Again, we've done this before last year, but I'll go over a couple with you. Okay, state the formula. We did all that in the other set of notes, like in your PowerPoint. EK, it's also on your formula sheet. EK equals 1/2 mv squared. So now, like if you're finding kinetic energy of a cyclist, so this is its V, but it has to be in meters per second. So we divide by 3.6, and we get 6.94 meters per second. Okay, and just remember the reason I can divide by 3.6 is because really I'm timesing by 1,000, because there's 1,000 meters in a kilometer, and I'm dividing by 3,600 because there's that many seconds in an hour. So like instead of just doing it all out, I just did it kind of one step. Either way, make sure you show your work and stuff. Well, I guess you don't have to really show your work for anything now. Just make sure, like when you're putting in the answer and stuff, like you're always converting things to meters per second, and so on. And so now the total mass is 86 kilograms. That's in the right units. So now we write down our formula: 1/2 mv squared. Put our numbers in. So we got 1/2 times the mass, 86.0 kilograms, times 6.94 meters per second. Remember, like when I divide this out, like this number has more to it. Use the whole number in there to get our answer of 2.07. It'd be times 10 to the 3 joules, or we'll just convert it to kilojoules right then. Okay, by dividing it by 1,000. Okay, an arrow flight has a kinetic energy of 170 joules, so that's our EK. Okay, if the arrow has a mass of 65 grams, so we have to divide that by 1,000, so we get 0.0650 kilograms. What is its speed? So with our formula, EK equals 1/2 mv squared. Okay, if I want to isolate V, I'm going to times both sides by 2. That will cross out there. I'm going to divide both sides by M. That crosses out that. So I got V squared is equal to 2EK over M. To get rid of the squared, I'm going to square root both sides. That cancels with that. So I get V is equal to square root of 2 times the kinetic energy divided by our mass. Now I'll put our numbers in. Okay, and our answer is 72.3 meters per second. So again, like for this, it doesn't ask us, like it just asks us for a speed. Okay, so we put in, sometimes you just have to be careful. It might say, like, what is the speed in kilometers per hour? You would now convert it at this point back to kilometers per hour. Okay, last question here for this video. I know it's getting long, okay, but like you can skip through it and just do the examples that you need. Okay, a 1,920 kilogram car, so that's our mass. Okay, brakes from a speed of 100 kilometers per hour. Okay, that's going to be one of our V's, 250 kilometers per hour. How much does the kinetic energy change? Where do you suppose it goes? So really, we're going to use both these, and we're going to find its kinetic energy initial, and then its kinetic energy final, and then subtract them to see how much it changes. Okay, and so we'll just use EK equals 1/2 our mass 9,200 or 1,920 kilograms times our initial velocity. Again, I divide it by 3.6, so I get 27.8 meters per second, and I'm going to square that. So our EK is equal to 741 kilojoules. So that's our initial energy that the vehicle has. And then it's slowing down. The mass doesn't change, but our velocity or our speed changes. It goes down to 13.9 meters per second. So our final EK is equal to 185 kilojoules. So the change is just going to be to subtract one from the other. And we got 556 kilojoules. Okay, and where does this energy go? Okay, it goes to, like, there's some that's lost to friction between the tires and the road. Lots of it's lost to heat in your brakes. Okay, as the brake pads squeeze the calipers, or onto your rotor and so on. Okay, that's where all their energy goes. So really, most of it's lost to heat. Okay, either to the friction between the tires and the road, or friction between our brakes and our rotors. All right, let me know if you have any questions. I can do examples right off of your worksheet if you need me to. Just let me know, and I'll make a short video with just one example on it if you need that. All right,